Penuh kesungguhan Akademi YouTuber Malaysia Rangka laksana dengan jitu Penuh bermisi Guru Ayu Mencapai misi yang satu Permisi kita bantu.
Tahniah. Siaran langsung ini dibawakan khas kepada anda oleh Akademi YouTuber Malaysia. Tumpukan perhatian anda. Siaran langsung akan bermula sebentar lagi. Link sijil akan diberikan di hujung siaran ini. Pastikan diisi dalam tempoh yang ditetapkan. Terima kasih.
Hai semua. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera, selamat petang dan selamat datang ke Pusat Tuisyen Percuma Akademi YouTuber Malaysia AYU. Bermula percuma, selamanya percuma. Buah durian, buah jambu, lebih enak lagi buah duku. Mari belajar bersama AYU, rajin belajar, bertambah ilmu. Bismillahirrahmanirrahim. Apa khabar anak-anak pelajar, guru-guru dari seluruh Malaysia? Anda bersama dengan kami. Selamat datang sekali lagi petang ini bersama dengan kelas tuisyen percuma Akademi YouTuber untuk subjek fizik SPM. Okay, kita ada di sana presenter kita, Mr.Peh. Hai Mr.Peh.
Hai, hello.
Dan kita juga ada Cikgu Kok selaku control host kita pada petang ini. Bagaimana cuaca di Melaka, Cikgu Kok, Mr.Peh?
Masih okey lah.
Okey, ya, masih okey.
Okey, diharapnya kita dapat berjalan lancarlah kelas kita pada petang ini. Okey, sebelum kita bermula kepada yang beragama Islam, ayo kita mulakan kelas dengan kitab Al-Fatihah. Dan pelajar yang bukan Muslim, anda bolehlah bertafakur mengikut kepercayaan masing-masing. Al-Fatihah. Amin, amin ya rabbal alamin. Okey, baiklah pelajar-pelajar semua, kita lihat dahulu siapa ada bersama kita di talian pada petang ini. Kita ada Syaing di sana, kita ada juga Cikgu Rina terus bersama-sama dengan kita. Jadi jom anak-anak pelajar ajak lagi kawan-kawan anda. Ramai-ramai lagi kita sertai kelas pada petang ini kerana hari ini kita akan belajar tajuk yang baru, iaitu kelas fizik tingkatan 5. Tajuk yang keempat, elektromagnetism. Kita akan bincangkan topik yang pertama, iaitu kelas ini akan dikendalikan dalam DLP, dalam Dwibahasa oleh Mr.Peh, iaitu tajuk dia 4.1, force in on a current-carrying conductor in a magnetic field. Tersasul sikit nak menyebutnya, panjang sangat. Okey, jadi diharap anak-anak dapat fokus dan silalah gunakan gambar profil yang bersesuaian, dan sekiranya anda ada soalan yang ingin ditanyakan kepada Mr.Peh, anda boleh type saja pada live chat dan juga respon kepada soalan-soalan yang akan dikemukakan oleh Mr.Peh sebentar lagi. Okey, jadi Mr.Peh adalah seorang guru di Kolej Tingkatan 6 Tun Fatimah Melaka, dan beliau juga selain daripada fizik juga mengajar kimia, iaitu chemistry. Okey. Jadi sangat banyak pengalaman, pernah mengajar banyak subjek termasuklah kepada hidup, RBT dan sebagainya. Okey, dan begitu juga Cikgu Kok, cikgu hebat kita di sana. Banyak video-video juga yang diterbitkan. Anda bolehlah layari channel Cikgu Kok dan juga channel Mr.Peh. Jangan lupa subscribe kepada yang belum subscribe. Okey, dan silalah berikan butang like kepada siaran kita pada petang ini. Okeylah, seperti biasa link sijil kita akan kongsikan di hujung siaran nanti bersama dengan link rekod kredit. Begitu juga dengan kod kelas yang akan cikgu berikan di sepanjang siaran ini. Okey, jadi sebelum cikgu serahkan kelas kepada Mr.Peh, okey, cikgu berikan dahulu dua kod yang pertama. Okey, anak-anak boleh dengar kodnya dengan baik. Yang pertama adalah A3. Okey, dua kod yang pertama A3. Okey, Mr.Peh, silakan.
Okay, so terima kasih kepada moderator Cikgu Hasita. So saya Cikgu Peh, kini mengajar di College Kadam 6 Tun Fatimah, Melaka. So berikut adalah kelas tuition percuma Fizik SPM. Sekarang untuk subjek tingkatan 4 kita sudah sampai tajuk 4, okay, 4.1. So keseimbangan terma. So disampaikan oleh Cikgu Faizal. Okay, so anda bolehlah pergi visit channel Cikgu Faizal untuk mendapatkan kelas tersebut. So hari ini Cikgu Peh saya adalah akan memulakan tajuk baru ini, tajuk 4 ke magnetan. Okay, so dengan subtitle yang pertama 4.1 Force on Current-carrying Conductor in Magnetic Field. Okay, so ini adalah panitia Fizik SPM Academic YouTuber. So bersama saya pada petang ini ada Cikgu Hasita dan juga Cikgu Ko. Terima kasih bersama saya pada petang ini. So di talian saya juga nampak ada Cikgu Rina. Okay, Cahaya, Cahaying. Okay, so welcome kepada kelas saya. Okay, so saya akan sampaikanlah, okay, seperti tadi saya mention. So chapter 4 electromagnetism with the first subtopic of chapter 4, which is force on current-carrying conductor in a magnetic field. Okay, so before we go to our chapter 4.1, so let us recall back what is the basic knowledge, okay, you have already learned in your PT3 level, okay? So this is actually related to the topic at Science Form 2, Section 7.3, which is also electromagnetism. Okay, so state the definition of magnetic and non-magnetic material. So first, you have to know what is the magnetic material and also non-magnetic material. So for magnetic material, it's a material that can be attracted by magnet. Here is some example, which is iron, nickel, and cobalt. Okay, then for non-magnetic material, there is the material that not attracted to magnet. So example here we have aluminium, copper. So aluminium and copper, although they are metal, but they have not able to attract by magnet, so they consider as non-magnetic material. Okay, so glass, wood, and brass. So brass is a alloy, so it's actually it's a metal. Okay, but here it is also not a magnetic material. Okay, so the definition for magnetic field will be a region where a magnetic material experiences force due to presence of magnet or current-carrying conductor. So that means the magnetic field is actually present at the magnet, but also a conductor, which is presence of the flow of electric. Okay, so it will form a temporary magnetism. So, but the magnet will be a permanent magnetism appear. Okay, so the permanent magnetic field will be almost like this. Okay, while for the current-carrying conductor, okay, so the magnetic field will be like this. Okay, so you need to able to see if you using the ion filling. Okay, so the pattern of the magnetic field around the magnet can be shown by using ion filling. So this is an experiment you conduct in your PT3 level. Okay, so for the direction of the magnetic field, you have to show by using compass. Okay, so this is a very simple experiment. Okay, so you have to understand before you go to our subtitle today. Okay, so define electromagnet. So electromagnet is a magnet effect that occurs when current is flow. Okay, so as I mentioned, the conductor without any current, so there will not have any magnet effect. Okay, so with the presence or flow of the current, so the temporary magnetism will be appear for the conductor with the flow of current. Okay, so when a current flow through a coin, so here is a coin, the soft iron core, so that means the new here will become electromagnet, so can be attract the metal clip here. Okay. Okay, so when the current in the coin is switched off, okay, so the soft iron core will be losses its magnetism. So that means the electromagnetism effect, okay, will be temporary for the current carrying conductor. When we switch off or we not provide any current, so the electromagnetism will be lost for the current carrying conductor. But for the permanent magnet, sure, the magnetism will always there. Okay. Okay, so magnetic field produced by current flow in. So during the syllabus of PT3 Science Form 2, okay, you already learned. So the magnetic field produced by the current when flowing to straight wire, okay, straight wire, coin, and also the solenoid. Okay, so here is the knowledge you already learned and you will be applied in today's lesson also. Okay, so thick cardboard sprinkles with iron filling, as I mentioned. If you want to see the pattern of the magnetic field for the current carrying conductor, you have to use the iron filling. Okay, so you will see there is a circular shape, okay, around the wire, okay, will be here. Okay, and then we will using the compass to determine the direction for the magnetic field produced by the current-carrying conductor here. Okay, so besides that, we actually can using the rule of right-hand grips rule, okay, to determine the direction of the magnetic field. Okay, so basically the right-hand grips rule will be like this. Okay, so your thumb, okay, your thumbs will be showing the direction of the current. Okay, your thumb will be showing the direction for current, and others 4 fingers will be represent for the direction of the magnetic field. So the symbol here, I for current, B for the magnetic field. Okay. Okay, so here I mentioned already lah. So the thumb represent the current direction, while the others finger represent for the direction for magnetic field. Okay, so another knowledge you have to know is the symbol. Okay, when you see there is a dot, okay, in the center of the magnetic field here, this will represent the current flow out from the paper. Okay, so this is a dot, and the cross represent the cross flow out from the paper. So this is what you actually already learned in your PT3. Okay. Okay, so here you can see the current is flow out of the paper. Okay, so we're using the dot to represent this is the out from paper. Okay, so with applying the right hand grips rule, okay, so your thumbs will be up. Then you observe your other's finger, okay, will be in anti-clockwise. So that means the here will be anti-clockwise. Okay. Okay, so the same theory will be applied at the current flow in the coin. So that means this is a coin. Okay, and here you can see the current is flowing from the positive. So it will be same as this example just now. So the current will be flow from positive to negative. Okay, so you will see the current will be flow out of the paper lah. Okay, so they will be reversed if the terminal is reversed lah. Okay, so here also the same current will be flow from out of the paper at here. Okay, and here will be into the paper. Okay, so into the paper we're using symbol cross. Out of the paper we're using symbol dot. Okay. Okay, so again we're using the right hand grip rule to determine the direction for both sides of the coin. So from here, as mentioned just now, so if this is the dot, so we're using the right hand grip rule out of the paper. You can see the direction will be anti-clockwise. Okay, so you can see this area, so the current throughout the magnetic field will be anti-clockwise. So here you see the arrow will be anti-clockwise. Okay, here. Okay, then for here, this part, so the current is into the paper. Okay, so our right hand gives through, the thumbs will be go down. So you observe your hand on top here. Okay, you can see your hand is, and other finger will be shows the clockwise. Okay, so you can see here will be clockwise lah. Okay, so seeing these two parts, right and left here, both will be go up. So this middle area, okay, all the magnetic field line will be go to up lah. Okay, okay, so again here as I mentioned, okay, so we're using the right hand grip rule, then the dot showing that the current flow up. So the direction for the magnetic field line at this area will be anti-clockwise. Okay, on the other hand, so the right side, okay, so the current is flow into the paper. Okay, so that means your hand will be thumbs to down, right? Okay, so you can see your other finger here will be, okay, will be clockwise lah. Okay, so we clockwise, so we here. And the middle part, as mentioned, both sides is move up right at this part, middle part. So the magnetic field line here will be go to up lah. Okay, and this will be also, you will see later on, okay, at our subtopic discussion. Okay, so the extension knowledge will be the magnetic field. Coin this will be applied at the caterpillar's field. Okay, so later on we will see together. Okay, and then the last, the solenoid. Okay, you also learned already at your Form 2. Okay, so the cardboard sprinkles with iron filling here. Okay, so you observe the magnetic field pattern will be like this now. Huh? Okay. Okay, so here we're using also the right hand grip rule. Okay, but this is a difference between the application on wire, straight wire and coin lah. Okay, so at here, the thumbs will be represent the north pole direction. Okay, and your other fingers will showing the current flow. Okay, it will be like this now. Huh? You can see. Okay, so you can see the thumbs showing the north direction for the magnetic field, and your other four fingers here, which will be the direction of current. So you can see the current is flow up, so your fingers will be up like this lah. Okay, so when your finger showing this, your thumbs showing at the left in this case. So the left will be north pole. Okay. Okay, so let us have a practice, okay, for this section. Okay, so draw the following direction of needle of the compass and the pattern. So the question here asks you to draw direction for the compass lah, in the compass and the pattern of magnetic field. Okay, so here is what we want to know. Okay, so again, at here you can see the current flowing from positive to negative. So the current will be flow into the paper. Okay, so into the paper, that means here we will using right hand grip screw. Okay, your thumbs will be go down. Okay, and then you observe your other finger. So you see that your other finger is in the clockwise direction. So here will be clockwise direction. Okay, so here will be clockwise lah. Okay, so from here you can see the direction here will be, this will be moved down. Here will be go to the left. Here you can observe, here will be go to up, and here will be go to the right. So this showing that this is the direction of the magnetic field for this case lah. Okay, so using right hand grip screw, your thumbs points to down. Okay, the other finger showing that. Okay, so to observe your other fingers, okay, you can see the other finger will be showing the clockwise direction. Okay, which is clockwise lah. So your pattern will be like this. As mentioned, the close represent the current flow into the paper. Okay, and then this is the direction I already discussed with you. Okay, the next will be also the current flow in the straight wire. So here, the changes here will be the terminal of the batteries change. Okay, here you can see the current will be flow from terminal, positive at down, and then go up, okay, from paper. Okay, so that means go out from paper, we will using the symbol dot. Okay, so again, we're using our right hand grip screw. Now our thumb point up and you observe, okay, your finger, not my finger lah, your fingers. Okay, you can see your other fingers is at the anti-clockwise direction. Okay, so thumbs up will be like this. You can see your others fingers, others 4 fingers okay, will be anti-clockwise. So when you draw, will be like this, anti-clockwise. So that means the compass at here will be up. Then at here will be go to left. Here will be go down. And here will be go to the right side. Okay, so the same. Okay, so the same answer will be, you have to draw your pattern magnetic field anti-clockwise, and the center must be a dot lah. Okay, because the dot represents the current flow out. Okay, so the direction for the compass will be as per discussion. This is the anti-clockwise lah. Okay, so from here we are quite clear that, okay, when the current flow out of the paper, okay, this is a close, right? So you can see the current, the magnetic field direction will be in clockwise direction. Okay, and then another, you can see when the current is flow out of the paper. Okay, so the direction of the magnetic field will be anti-clockwise. Okay, so the next, draw the following direction of the compass also and the pattern for the case in the circular coin here. Okay, so here you can see the current flow from positive terminal, here also out of the paper. Okay, as mentioned, out of the paper, we're using dot, okay, and here we're using go in, we'll go using the close lah. Okay, so again, you see, as I mentioned, when the paper is go up, so it will showing anti-clockwise. Okay, you can use again your right hands. Okay, okay, so again, go up, thumbs up. You can observe your other fingers, which is the anti-clockwise. Okay, so will be like this lah. So anti-clockwise will be here. So for sure that this will be go up, this will be go down, okay, which is this one and this one. And the anti-clockwise pattern for the magnetic field will be here. Okay, will be this part. Okay, and here, go down. When go down, go into, so that means our hand will be, the thumbs will be go down. Okay, like this. Okay, and you can observe your other fingers. There is a clockwise direction. Okay, so will be here. Clockwise. So here will be down. Here will be up. Will be like this. And at the center here, we are showing the close with the clockwise direction of the magnetic field line here. Okay, and at the center, so go up because at here is anti-clockwise, and here is clockwise. At middle, they're showing all is go up. So we are showing this line. So overall, this is the pattern of the magnetic field line for the current flow into the coin at this coin direction. If I say the battery reverse, definitely the answer will be reverse also. Okay. Okay, the next will be draw the flowing direction of the needle compass and pattern in the case where the current flow into the solenoid. Okay, solenoid will be current curving like this, so become coin. Okay, so at here we will be using the right hand grip screw also, but here the thumbs will be represent the direction of north pole for the magnetic field, and your other fingers will be the direction for the current. So here you can see the current is move up. So your hand will be move up. Okay. Okay. So again, here you can see I already mentioned to you. So although this is also a right hand grip screw, but applying the theory in solenoid, so your thumbs will be showing the direction for the north. Okay. But here for sure that we have to identify the direction for north. And the question given us the direction for the current, which you have to use your other fingers, okay, to find your position of thumb, which is the position of the north pole for the magnetic field. Okay, so here, okay, so my hand will be almost like this now. Okay, so you move up. Okay, you look at my hand will be wrong. Okay, you look at the screen. Okay, so your hand will be moved up for others 4 fingers here, not the thumb, 4 fingers. Okay, so here you can see your thumbs will be point to the left. So that means here will be the north. Okay, and here will be the south. Okay, so here there is another, okay, here I mentioned already, this is the direction for the current, and your thumbs showing the direction for the north pole of the magnetic field. Okay. Okay, so here you have a, okay, so here is north, here is the south. So here you have another knowledge you already learned also at your Form 2 syllabus. Okay, so you can see when here is a north, here is a south. So the direction for the magnetic field is come out from the north and then back to south. So it will be like this. Okay, so that means here will be like this. Here will be like this. Then move to back. Okay, here also the same. Will be back to back to the south. Okay, so we are very sure that here the current, the direction for the magnetic field will be up. Okay, it will be like this. You can see here up. And then at here will be to the right, because the magnetic field line will be come up from the north to the south. So here will be go in, and here will be go to the right, just like this lah. Okay. Okay, so you will get wait. Okay, I think this is a mistake here. So this will be go to the right. Okay, as mentioned, this one. Okay, and then here also, this one also is mistake. Should be go to the right also. Okay, but this two is correct. Okay, so you have to accept the answer here, which is go to the right for these two position. Okay. Okay, so I have already finished the recall section, which will be applied in our subtopic today. And this subtopic is quite long. Okay, and we have the 6 learning standard in this subtopic. Okay, so we take some time for today's lesson. Okay. Okay, so for the first learning standard, okay, so here describe the effect of the current carrying conductor in a magnetic field. Okay, so we have already learning the current carrying conductor will be produce a temporary magnetic effect, right? So this is a Form 2 what you have already learned. Okay, so what you learn in the Form 2 syllabus, okay, PT3 level, there is only the single magnetic field in your syllabus, where either there is a permanent magnetic field, okay, or there is a temporary magnetic field produced by the current carrying conductor. Okay, so for the permanent magnetic field in magnetic magnet, just now I already give the example where the direction of the magnetic field will become from the north to the south. So this will be applied in your Form 5, this subtopic lah. Another one will be the current carrying conductor. Okay, so here will be discussed also. Okay, but for this syllabus, we want to see if the current carrying conductor is put together with the permanent magnet. So what is the effect? Okay, when two magnetic field is appear together. Okay, in our subtopic. This subtopic and learning standard 1. Okay, so effect of the current carrying conductor in a magnetic field. Okay, so the magnetic field here can be both is a current carrying conductor, okay, or one is a current carrying conductor, another one is a permanent magnetic field. Okay, so in this we discuss one conductor in permanent magnet. Okay, so an electric current carrying conductor produce magnetic field around it. So this one we already discussed lah. Okay, when the current flow through a conductor, okay, so the temporary magnetic effect will be appear. Okay, you can observe by using the iron filling. Then the direction you can using right hand grip screw, you can using compass, okay, to get the direction. Okay, so you need on the power, because I mentioned the current flow will cause the conductor produce the magnetic field. Without current, so the conductor do not produce any magnetic effect. Okay, so if the current carrying conductor in another magnetic field, so here you can see, so the wire here, short copper wire carrying current. So when we on, so there is a current flow from the positive terminal to negative terminal. So the flow will be like this lah. So that means there will be a temporary magnetic field appear, okay, at the copper wire here. Okay, and then you can see here we have another magnetic field. Okay, this is a permanent magnetic field. Okay. Okay, so here the copper wire showing the current carrying conductor, which is a temporary magnetic field, and the permanent magnetic field will be produced by the permanent magnet here lah. Okay, so that means here we have two magnetic field. So what is the effect? Okay, you can look at the statement here. A force will be add on the conductor. So that means there will be a force applied on the copper wire here. Okay, so the copper wire will be moving. So move to the right or to the left. Okay, so this is the effect. Okay, in this case, will be go to the right lah. Okay, why? Later on we discuss. Okay, so just let you know the effect for the two magnetic field will be a force applied. Okay, it will be a force will be acting on the conductor, will be produced. Okay, so here, as I mentioned, okay, so we will be discuss two magnetic field in our subtopic today. Okay, so the first will be the magnetic field for the permanent magnet, in this case and the second will be the current carrying conductor, which is produced by the copper wire here when the current flow through. Okay, so we finish lah. So the first learning standard we know lah. So the effect will be force produced. Okay, so the learning standard 2. Okay, so we need to draw the pattern of combined magnetic field. So the combined magnetic field we know as catapult field. Okay, to indicate the direction of the force on the current carrying conductor in a magnetic field. Okay, so here will be you can using the draw of the pattern of the catapult field here to indicate the direction, or you can using a new theory here, which is a Fleming left-hand rule. Okay, so define catapult field. So catapult field occur when there is an interaction between two magnetic fields. So the action between the permanent magnetic field and the magnetic field produced by current carrying conductor will result in a resultant field. So we know as catapult field. Okay, so the catapult field, that means there is two magnetic field acting together, okay, or interact together. Okay, so there are three types of the catapult field. Okay, so first will be the two interaction magnetic field between two wire. Okay, and then second will be the single wire in a magnetic field. Okay, so this is an example I showing you at the learning center 1 just now. Okay, another one will be a coin in a magnetic field. So the coin will be here. Okay. Okay, so let us see together the pattern of the catapult field in two wire. Okay, so when current flow in a wire, a magnetic field is produced around the wire. This one we know already lah. Okay, this is a syllabus PT3. Okay, if two conductors placed close together, then the field of one wire affect the others, and the force will be exists between the two wires. So as I mentioned, if there is a catapult field, that means there is a two magnetic field interact together. So the force will be acting on the wire lah here. Okay. Okay. In this case, the wire can be flow in the same direction. In this case. Okay. So two parallel conductor, each of which carry a current in the same direction will attract. Okay. So in this case, you can see. So the current both direction is the same. Here I given the example of both flow up lah. Okay, flow out from the paper. Okay, so you can see the force will be go in for both. So that means they will be attract to one another's. Okay, so if let's say for the case, the current flow into the paper, so will be showing the same attraction also. Okay. Okay, so why? Okay, you can see at the left position here, this is a dot. So the dot showing that the paper, the current flow out from the paper. Okay, so with your right hand grip rule, you already learned, and we have already recalled, okay, at your PT3 syllabus. Okay, so your hand will be go up. Okay, and you can observe your other finger. Okay, they will be anti-clockwise here. Okay, so here you will be also the same. So this is the flow up from paper. Okay, so will be also anti-clockwise. Okay, so when there is a two field interact together, force will be produced lah. Okay, okay. So why the force will be moved to this position? Okay, so this is because opposite magnetic field will be showing the weak magnetic field. Okay, so here again I zoom in. You see the arrow here will be up. I already showing with the right arrow here, and here the arrow will be down. So you can see this is the opposite magnetic field. So when there is an opposite magnetic field, so here will be a weak magnetic field here. Okay. So on the other hand, you can see at this position, so both sides showing there is a same direction. So that means here will be, at these two positions will be a strong magnetic field. Okay. So the force will be acting from the stronger position here to weaker position. So you can see in this case, the stronger position is at the blue box area here. And then the green color here will be the weak position, weak region, weak magnetic field region. So the arrow will be moved to right for this for here lah. So for here, the strong magnetic field will be here, and here will be weak. So the arrow show to the left, okay, because the force will be from the stronger region to weaker region. So you can see both of the F is attract together. Okay, so you can see here, two parallel conductor, each of which carry a current in same direction, will attract one another. Okay. Okay, so another case, okay, here catapult field is produced, wire is being catapulted from strong field region to weak field region, just like I mentioned already. So that means the force will be adding from strong to weak region. So we appear this. Okay, so we attract in this case where the current flow in the same direction. Okay, so we have another case. Okay, so this case you can see the pattern is actually almost same with the magnetic field you learned in PD3 just now I show you, where the pattern, the current flow in the coin. Okay, okay, so the two conductor which carry the current in opposite direction. Okay, so I show you here. You can see here the current flow out. Here, the current flow in. So that means here will be opposite direction. Okay, so they will repel. You see the F will be repel to right and left here. Okay. So at here, dot showing that the current out of the paper. Out of the paper. So thumbs up here, wrong already. Okay, thumbs up. Okay, so you can see your fingers, others fingers will be anti-clockwise, will be shown like this here at here. Okay, and then another side, okay, close, showing that this is move into the paper. Okay, so your thumbs will be down. Okay, so down, and you observe from the top, you can see your hand is clockwise here. Okay. Okay, so this is similar what you learned at your revision just now, right? I showed you already. Okay, you see, will be this. But during your Form 2 syllabus, we not discuss about the catapult field and produce a force. We just showing the pattern only. Okay, so but here, the wire different here showing the same pattern. okay, different position of the current flow, showing actually almost the same pattern here. Okay, so here you can see here will be the strong magnetic field because all the line here showing same direction. Okay, maybe you will ask me, did you here also you see here also the same direction? Here is also the same direction. So that means all is in the same direction. But when we see the magnetic field line which closer to each other, okay, so here will be showing that this is a strong magnetic field. Another one, because the wire is very close at this area, so when the area where the magnetic field is close to the wire, they will be have the stronger magnetic field. So that means here will be weak. Although here is showing that this is the same direction. Okay, but compared to the middle, okay, so you can see the magnetic field line here is very close together and this area is close to the wire. So definitely for this comparison, okay, so the magnetic field will be strong at the middle and weak at this area and also this area. Okay, so that means here you can see the force here will be from the weak, actually from the strong region, which is stated in blue box here to here. And here also from the strong to weak. So overall, here we see they will be repelled to each others. Okay, so this is what you can see here lah. Okay. Okay, so the next, so it's the catapult field for single wire in magnetic field. Okay, so this one is the example I showed in Learning Center 1 just now. Okay, will be this lah. So single wire in a magnetic field will also produce a force. Okay, in Learning Center 1, we know already the interaction between two magnetic field will be produce a force. Okay, not only a force produce force. In another case later I show you, actually there is a couple of the force lah. Okay, so but here single wire in a permanent magnetic field will be a force also lah. Okay, so here magnetic field by the current carrying conductor will be here. As I mentioned, the current will flow from the positive to here to here. Okay, will be current flow like this lah, with this red arrow here. Okay, so you can see if let's say we observe from our screen, the arrow is moved into the screen, right? So it will be into the paper lah. So it will be close, and when close, will be down. Okay, and you can see your fingers lah. Other finger will be showing that this is a clockwise direction. It will be like this. So thumbs will be go down, and you see your other fingers will be clockwise for this case lah. Okay, so this is a magnetic field for the current carrying conductor here. Okay, and then the second, so the permanent magnet, okay, as I mentioned just now, will be moving from north to south. Okay, here. So it will be like this lah. Magnetic field line move from the north pole to the south pole. So combination of these two magnetic field will be produce a catapult field lah. Okay, so you can see we combine these two together, will be like this. Okay, so will be like this. So the blue color line showing that this is a permanent magnet, which is moving from the north to the south. And then for the current carrying conductor, when the current move into, okay, so they will be clockwise direction. Okay, then we look at this part. Okay, I boxed in blue already. Okay, you can see. So the red color line move up, blue color line also move up. As I mentioned, when there is the same direction of the field line, there will be a strong region. So here will be the strong region. Okay, so on the other hand, okay, as I mentioned, magnetic field line in same direction will be strong magnetic field. Okay, and then the another side, the green color, okay, so we observe again. You can see the blue color, which is the permanent magnetic field line, will be go up, and the red color, you see, move down, right? So this is the opposite direction, so showing that this is the weak region. Okay, so weak region. And again, we apply just now the force acting will be from the strong region to weak region. Okay, so will be like this lah. And when we draw, the strong region area will be have more magnetic field line compared to the weaker region. Okay, so you can draw actually 3 lines enough already, as long as the strong region showing more line compared to the weak region. So the force will be to the right. Okay, so the catapult field is produced, will be this lah. So wire is being catapulted from strong field region to weak field region. So the resulting force will be to the right. So you can see will be move to the right. So that's why just now in learning standard 1, I told you the force will be adding to the right. So this is the first method you can use. Okay, so this method will be take time lah, okay, to find out the direction of the force. Okay, so you can see, okay, so we can do one practice before we go to second method. Okay, so draw the resultant magnetic field pattern and direction of the force produced in the diagram below. Okay, so here first, here this is a dot, so showing me that this is out of the paper. Second, we see there is a permanent magnet here. So here we have the field from the north to the south here. Okay, okay. So for first step, as I mentioned, simple dot. Okay, so this is a magnetic field pattern. Will be showing by the current-carrying conductor. So dot showing that this is a move up. Okay, here wrong already. Move up actually. Okay, move up. So right hand gives rule, move up, out of the paper. Your paper must be on your table, right? So move up. Okay, so be thumbs up. You can see your other's finger will be anti-clockwise lah. Okay, so if you want to draw, will be okay like this lah, anti-clockwise. Okay, and the second field will be permanent magnet, will be moved from the north to south, will be like this. Okay, so resultant will be a catapult field lah. So the catapult fields will be like this. Okay, so here you have to, okay, so the black color arrow showing that this is a permanent magnetic field line. Red color will be the current-carrying conductor magnetic field line here. Okay, so again we observe the top. Okay, so you can see, okay, you cannot see clearly, right? So I zoom in, you can see. So here, black color, red color, you see the arrow showing that this is move to the left. So this is the opposite direction. So green color area here will be the weak region. So you can actually straight away look at here also can. No need to draw this also can. Okay, so from here you can see the direction for the current-carrying conductor magnetic field will be moved to the left. Here will be to the right. So opposite direction. So this will be weak region. Okay, and then you observe the blue color region here. Okay, so you will see both will be at the same direction. So curve down will be moved to the right. Both will be at the same direction. Okay, so here will be same at, you can straight away look at here. So here will be both move at the same direction. So there will be a strong region. Okay, so that means the force will be from strong to weak. So you have to draw and the strong region have more magnetic field line, and the weak region will be less lah. Okay, so you can draw here, represent the current carrying conductor magnetic field line here also lah. Okay, so the answer will be this lah. Okay, so the next will be the framing left hand rule. Will be more easier actually, but here I think you have to imagine lah. Okay, so we using the framing left hand rule to determine the direction of the magnetic field, magnetic force. Okay, so this will be the framing left hand rule. Okay, so you make sure all your fingers is in the perpendicular to each other lah. Will be like this lah. So you can look at the figure here. Okay, so your thumbs will be showing the direction for the force. Your first finger here will be represent for the magnetic field. Second finger will be represent for direction of the current. Okay, so the direction of the magnetic force will be changed when the direction of the magnetic field and current is changed. So that means the direction for the force will be changed if these two directions is changed. Okay, so in this case, I apply the same case lah. So firstly, okay, so you have to take out your hand and prepare as this position lah. So all the fingers here will be perpendicular to each other lah. Here, make sure Okay, so here current flow in will be here. Flow in now. Okay, and then magnetic field direction will be up lah, because of north to south. Okay, will be this. So when you position your current in, then your first finger for magnetic field up. So your thumb will be at the right position. Will be like this. When you see me, definitely will be opposite lah. Okay, will be this. Okay, you have to show by yourself lah. So you will see here, answer will be same as the just now one. Okay, so we can actually using framing left hand rule to determine the direction more easier. Okay, so the answer will be right. Okay, and then for the checkpoint 4.1, okay, so here the diagram shows the brass rod is placed in the magnetic field and permanent field. So magnetic field will be conductor lah. Permanent will be here. So in which direction does the brass rod move when the switch is closed? So when switch closed, current will be flow from positive to negative. Will be here. Okay, so switch off, that means there is the temporary magnetic field produced by the current carrying conductor here. Here will be the brass rod. So in the permanent magnet here. So here will be two magnetic field here. Okay, so the catapult field will be appear here lah. Okay, so the current will be flow from positive to negative. Okay, so will be this. So your second finger will be the direction of the current. Okay, so your hand will be like this. Then your current will move up like this. Okay, and the direction for the magnetic field will be from north to south, will be up. So move. So your second finger move to yourself, point to yourself. Then your first fingers will be up like this. Will be like this position now. Okay, so your thumb will be showing. Okay, this is the magnetic field. Your thumb will be showing at the left lah. So that means the roots will be moved at the D direction. Okay, so the answer will be D. Okay, so this is 4.1 checkpoint question number 4. Okay, so here the diagram show the current flow in the conductor in the direction into the pitch. Okay, which is the direction of the force adding on the conductor. Okay, so here will be move in because of the close symbol here. Okay, then second, you can see, okay, so here simple close means the current flow into. So here your second fingers will be into. Okay, then will be positioned like this. Your fingers into. And then the next will be the direction of the magnetic field. So will be from north to south. So that means your second fingers current move in. Then your first fingers here will be to the left. Then you see your hand, your thumbs will be at the up already. So there is points up. So the position will be A. Okay, so the next question 5 here is 2016 question. Okay, so here we also applying the same theory. So 28.1 show the permanent magnet. Okay, so this is a magnetic field. So it will be from the north to the south. Okay, and then here will be move into. Okay, move into, right? Okay, so you can using the two method to get your answer lah. But here I advise you using the Fleming left-hand rule, more easy. Okay, so which diagram is correct when the current-carrying conductor is placed into the permanent magnetic field? So we place this into lah. So that means the catapult field will appear lah. Okay, so this is what I mentioned just now. Okay, again using your Fleming left-hand rule, your left hand. So first the current move in. Okay, move into the screen, your screen. Okay, and then the second finger move into your screen, and then the first fingers will be go down. Okay, so you can see move into the screen, go down, your thumbs will be points to the left. Okay, so definitely C and D out lah, because here is right, so wrong. Okay, so it will be left A and B. Okay, so we'll think, okay, maybe the draw of the magnetic field line is incorrect, but here both also the same. Okay, so this is from weak to from strong to weak, right? Just now we mentioned from weak. Sorry, this one is reversed already. From correct lah, correct. Here is correct actually. Okay, it's correct. From the strong region to the weak region. So the line is correct. So what's the wrong here? So actually here wrong because of the direction of B. Okay, so you can see. Okay, so must from the north to south. So here is wrong. Here from south to north. So that means here A is wrong already. So the correct one must be from north to south. So the answer is B lah. Okay. Okay, so for learning standard 3, okay, sorry, this lesson quite long, okay, for today's. Okay, so soalan SPM. Okay, so I get for Hamba Allah. Actually, I get from SPM this question. Okay. Okay, so learning standard 3, factor affecting the magnetic field, magnetic of the force. Just how we mentioned that when there is a catapult fields, so the magnetic force will be produced lah. Okay, so what's the factor affecting the magnetic of the force on the acting on the conductor? Okay, so here you can see the first will be here. The first will be a large force will be required to drive a motor in the washing machine. So here we have the 2 motor. So we need a large force, but sometimes we need to have the smaller force when we apply in the cooling fan here. Okay, so that means we have to know the factor and what to adjust so that we get large force or smaller force for the particular work we want to do lah. So here the factor we have to know lah, so that we can get the correct magnetic force which is applied in the large force and the smallest force for the certain of the work. Okay. Okay, so here the first will be the magnetic strength. Okay, so when the strength of the magnetic field increases, so the force adding will be increases. Okay, so how we can increase the magnetic field, the strength of the magnetic field? So here we have 2 ways. So first, we have to place our magnet close to each other. Okay, so that the gap here will be smaller. Sorry, the gap here will be smaller. Okay. Okay, second, we're using a powerful magnet so that we can get the strength of the magnetic field become stronger lah. So two-way. Okay, so next will be the magnitude of the current must be increased lah. Okay, to get greater force, the magnitude of current must be increased. So here we have also few way. We have four methods here. So first we have to using the thicker wire and shorter wire, because both of these cases will be reduce the resistance and a lot more current to flow. So the force will be increased lah. Then the third, we increase the power supply EMF so that the current flow will be also increased. The last will be we using the coin instead of the straight wire. Okay, so these four methods will be increase the magnitude of the current and then increase the strength of the magnetic field lah. Okay. Okay, so here is a question for 4.1. Okay, so diagram show the arrangement of the apparatus to study the effect of force on a current-carrying conductor in the magnetic field. So the wire move to the left at small angle. So you can see here, move to the left with small angle. So when the current flow into the conductor in the direction shown in diagram here, okay, you can see because of two magnetic field, so there is a force produced to the left. Okay, so what we need to do so that our wire will be moved to the right. And second, we need to have a bigger deflection. Okay, so we want to move to the right. Okay, so for move to the right, so according to the principle for the concept of framing left-hand rule, we have to change the direction for the current and also the direction of the magnet. Okay, so that means A and C is correct, where A changes the polarity for the magnet, C changes the direction of the current. Okay, then B is wrong because they maintain, so that means the position will be also the same, move to the left. Okay, then the question asks us to have the crater deflection, so that means we need to have the crater force here. Okay, so to have the crater force, as we discussed just now, okay, we need to increase the value of current. Okay, then this is the correct answer, A lah. Then C is wrong because we need to increase the strength of the magnet. So the answer is A. Okay, so easy. We have the break for
okay, boleh. Okey, pelajar-pelajar semua jangan ke mana-mana. Kita berehat seketika, kembali lagi selepas ini.
Tuisyen online percuma. Tuisyen online percuma. Layari www.academyyoutuber bagi mengikuti tuisyen online secara percuma. Prasekolah, sekolah rendah, sekolah menengah, semua ada di Akademi YouTuber. Rujuk jadual di laman sesawang www.academyyoutuber.com. Semoga masa terluang anak-anak anda diisi dengan sebaiknya. Tuisyen online percuma mestilah Akademi YouTuber.
Okey, kita kembali lagi. Sebelum cikgu serahkan kembali kepada Mr.Peh, saya berikan dahulu dua kod yang seterusnya, iaitu dua. Okey, dua kod yang seterusnya, dua. Okey, Mr.Peh, teruskan.
Okay, so we go to our next learning standard. Actually, we still have 3 learning standard now. Okay, 4, 5, and 6. Okay, so I try to make it faster. Okay, so for the learning standard 4, describe the effect of the current-carrying coin in the magnetic field. Just now I already mentioned that the effect of two catapult field will be produce a force. Okay, so we discuss case where there is a two wire. So two wire, the current might be can in same direction or different direction. And second, I just now also already discussed with you the single wire. Okay, in a permanent magnet. Okay, so in this case, we will study the effect for a coin of the wire in the permanent magnet here. Okay, okay, so catapult field, a catapult force that produced from a current carrying coin in the magnet. Okay, so the diagram shows a current carrying rectangular coin. So it will be this, placed in a uniform magnetic field. So uniform magnetic field will be here lah. So it will be here. So that means when the current flow from here, okay, to here, so there will be two magnetic field adding or interact together lah. So the catapult field will be produced. Okay, so what is the difference between the catapult field? In this case, for another previous one lah, we just now we learned in the previous learning standard. Okay, so here you can see. So the magnetic field of magnet, so the magnet showing that this is a permanent magnet lah. Okay, so the current carrying conductor are combined to produce two catapult fields. So you see here we have two catapult fields. So just now we have single catapult field. Here we have two. Okay. Okay, so since the current in both sides of the coin flow in opposite direction, okay, so you can see the current one is moved in for AB, and then out is from CD. Okay, so the two forces in the opposite direction constitute a couple which produce a turning effect to make the coin rotate. Okay, so the effect here will be two couple force in different direction. So we will see there is a rotation. Okay, actually it's also the force, not a force, two forces is actually produced, and they are in the opposite direction. So we will see a rotation is the effect for this catapult field. Okay, so this is what I want to discuss here. Okay, so understand the catapult force that produced from a current carrying coin in a magnet. Okay, so you can see in the diagram shows a current carrying coin with permanent magnet. So it will be this lah. Okay, here and here will be permanent. So current that flow in a coin produce a magnetic field. So here will be another field lah, current carrying conductor lah, just in the coin. Okay, coin form. Just now we discussed a straight wire. So now it's coin. So the direction of the current on AB is opposite as CD. So AB is moved in, then the CD is moved out. Okay, so again, we're using the Fleming left-hand rule. Okay, so the current move in, okay, will be here. Will be here. Okay, and second, you can see the magnetic field will be from B, from N to S lah, so be here. Okay, so that means when the current flow in at your second fingers, and the magnetic field is from north to south. Okay, so you can see your thumb will be point to down, so be same as the direction showing here lah. Okay. So, and now we discuss another side. You see, we erase first. Okay, so another side. Okay, so here we down as we get just now. So here, there is another side. We also using the Fleming left-hand rule. So here the current is moved out. So we'll be showing at your second fingers. Then the direction for the magnetic field will be the same also from the north to south. So current move out of your screen, current from north to south. So you can see your thumb will be points up. Okay, so it will be like this lah. So there is two forces actually acting on the conductor in different directions. So we can see it will be rotate lah. Okay, in this case it will be rotate in anti-clockwise lah. Yeah, anti-clockwise. Okay, so here is another method I showed you just now. We using the diagram to draw and identify the direction. Okay, so diagram B show the superposition of the two magnetic fields that occur on permanent magnet. So here we permanent magnet. And the current carrying coin, AB, and the CD. So AB will be into, you can see the arrow. So when into will be using your right hand grip rule. Okay, so you can see into will be clockwise. Okay, will be this at here. And then here will be up using right hand grip rule. Point to yourself. Okay, you can see your fingers will be, others fingers will be anti-clockwise will be here. Okay, okay, so from here, as I mentioned just now, okay, so here will be current into the paper. Okay, showing this will be the clockwise. Okay, so you can see at up position, at this position above the close now. So the two fields showing that in the same direction. So this is a strong region. Okay, so here just now we mentioned the force will be from strong to weak region. So we go down. Opposite will be here strong region. The opposite will be weak region. So be down. So we same as what we get in Fleming left hand rule. Another side. Okay, you can see here will be also you apply your right hand grip rule. So you get the carrying conductor will be anti-clockwise here. Okay, so again we see above. Okay, so you can see here when move to here will be to the left, and our permanent magnet will be still from north to south. So this is the opposite direction. So here will be weak region. So opposite must be strong region. So the force will be adding from strong to weak. So will be like this. So we get same result. Okay. Okay. So diagram C show the resultants of the magnetic field that occur from the interaction between the magnetic field on the permanent magnet here and the magnetic field on the current carrying coin. So it will be here and here. Okay. Okay. So both catapult force cause the coin to rotate in anti-clockwise, as I mentioned just now. Here will be move to here. Here we move to here, anti-clockwise. Okay. So when the direction of the current is reversed, the direction of the rotation of the coin is also reversed. Okay. Okay. So here we discuss the tuning effect on the current carrying rectangular coin can increase. So here we have 5 methods here. So the first, the numbers of turns in the coin. Okay, so when there is more numbers of coin, so the current will be more, so will be produce a larger force. Second, the strength of the magnetic field. Okay, so from the learning standard 3, we know already we can place our magnet closer and we're using a powerful magnet. Okay, so that the strength of the magnetic field will be increased, so the force adding on conductor will be increased. Okay, then the third, the magnetic current must be increased. So there is the 4 way we also mentioned just now in learning standard 3. We're using thicker wire, shorter wire, higher EMF supply, and use a coil of wire. 4 method. Okay, in learning standard 3, you can go back for the video after that. Okay. Okay, and then the area of the coin must be bigger. Okay, from this you can see B is the magnetic field. So with the bigger region, so the exposure or the more area will be adding or interact with the permanent magnetic field. So we need to have the more wider area of the coin. And then the last, we're using the semicircular shape permanent magnet. So why? Okay, because you want to get a radial field. So what is the radial field? So you can see there is a gap here. So for the shape of the semicircular, so the gap will be always parallel to the plane of the coin when it rotates. Okay, so that means the gate will be always the same. Okay, so when we increase the speed and we increase the current, so the speed of the rotation will be also increased. Okay, so this is the reason why we need to have the semicircular shape permanent magnet. Okay, so learning standard 5. Okay, so we want to describe working principle of the direct current motor here. Okay, okay, so firstly, we need to know the function of the DC motor structure. Okay, so here this is a DC motor structure. Okay, so they have the dry cell here. So to supply current to the coin, the function. Second, we have the permanent magnet here to produce a uniform magnetic field. So as we learn in this subtopic, we want to create a catapult field. We need to have two magnetic fields. Okay, so this is the first magnetic field. The second, coin. Okay, so electromagnetic is produced around the coin to create resultant magnetic field with permanent magnet. So this is a second magnetic field we want to produce lah. And here, this is a temporary magnetic field. They will be appear when current flow through lah. Okay, so the commutator will be here. Commutator. So I zoom in a bit. So the commutator will be here. The C here lah. The C here. Here will be commutator, and also the carbon brush lah, which is touching the commutator here. Okay. Okay. So the commutator invert the direction of the current on the coin for each half rotation, so that the coin continuously moving in same direction. So that means here is used to invert the direction of current. Okay, and then the last here will be the carbon brush. Okay, so the carbon brush is to maintain the current contact to the commutator, so that current can flow from the dry cell. Okay. Okay, so the working principle. Okay, so the main operating principle of the DC motor is the electromagnetic concept, where a current-carrying conductor placed in the magnetic field direction of the force determined by experience, force, and Fleming left-hand rule. Okay, so here the first position, here we have the different position here. Okay, so here we have the zero position. So the current flow through the carbon brush and the coin rotate in clockwise direction. So you can apply the same theory lah. Here, the current up, and then the magnetic field will be from here to here. Again, you using your Fleming left-hand rule. Current, your second fingers point to you, and the magnetic field at your first finger will be point to the right. So you can see your thumb up. So here, F will be up. And here, the current will be in. So current will be in. Then the magnetic field will be the same to the right. So you see your thumb will be go down. So it will be like this lah. Here will be clockwise direction. Okay, and then no current flow here because there is no touching for the carbon and commutator. So no current is flow, but it is still moving due to the inertia. Okay, and the position 180. Okay, so again you can see the direction will be current still maintained. Okay, because the function of the commutator already reversed the position of the coin. So that means the current flow is still the same here. Okay, so current will be up. Then the magnet will be the same from north to south. So here F will be up. Here the current in. Then the magnet to the N, from N to S. The U is N now, udara now. So you see your hand, your thumb will be point to down. So we still in the same direction. So this is a function for the commutator. Okay, so the last will be the same 270. So there is no current flow because the commutator and carbon brush is not touched to each other, rotate due to the inertia. So that means this is a first cycle lah. So the working principle is like this lah. Okay, then the learning standard 6. Okay, describe factor that affect the speed of the rotation in an electric motor. Okay, so firstly, we comparison between the brushless motor and brushless motor. So here, this is the figure lah. Here, this is represent the brush DC motor, which there is a commutator together with the carbon brush lah. But here, don't have any brush here for the brushless DC motor. Okay, the difference will be for the brushless will be no carbon brush and also no the commutator, as I mentioned already. And then here, the advantage for the brushless will be, there will be the no friction, high efficiency, and zero maintenance, last longer. So that means the brushless will be better lah. Okay, will be better. Okay, and disadvantage is this is very expensive. Best thing normally will be expensive, right? So we try what we can do to reduce the cost so we can benefit all the industrial lah. Okay, so the next will be the factor affecting the speed rotating the motor. So this one will be same as what we mentioned just now. This is a 5 factor I mentioned just now already. Okay. Okay, so the last question here. Okay, so diagram show the coil wire in the magnetic field. Okay, so how we can increase the rate of rotation? Okay, so first increase the current. So this one is correct lah, because current can increase the rotation. Okay, so the second is wrong. Okay, because the vertical length of the coil increase. So when the length of wire increase, so the resistance increase, current decrease. So the rotation will be decreased lah, because the force produced reduced. Then C, distance between the magnet must be close to one another lah, because we want to increase the strength. Okay, so here increase is wrong. We need decrease. Then the D also wrong, because the thickness of the magnet is not equal to powerful magnet. So the powerful magnet maybe is small. Okay, so the answer here will be A lah. Okay. Okay, so here is the last question for today's discussion. It's a 2013 paper 2, section A, question number 8, decision making. Okay, so here, diagram show 3 electric motor, design X, Y, Z. Here we have 3 design. So we want to build a small portable fan. Okay, so based on the diagram, state the suitable characteristic of an electric motor to be used to rotate fan in character speed. So the character speed means we need to have the character force. Okay, so here, first, the numbers of the turn. Here we have 50 and 10. Okay, so which one will be better? So we have to choose 50 lah. Okay, because the 50, more current, more turns of the coin, that means it will be more current will be flow. Okay, so the force produced will be larger. Okay, then the second, we compare the battery numbers. So here we have 3 and 1. So definitely we want 3. Okay, reason, the size of current in the conductor increases, the force will be increases lah. Then the third shape, we are using semicircular. As mentioned, we need to have the ratio field so that the speed rotation will be directly proportional to the current. And then definitely we will choose X lah for this. Okay, because the X meet our 3 requirements here. Okay, thank you everyone. This is my discussion today. Thank you.
Okay, thank you very much, Mr. Peh. Actually, I discussed this with Cikgu Kok just now. It's a quite long topic, so I think for next year maybe we can separate into 2 series. We can discuss this into 2 series, so we can focus more on the content standard and do more exercises, right? Okay, but never mind, students. Later you can go back to this video and check for each of the 6 learning standard discussed by Mr.Peh just now. Okay, you can pause at anywhere so you can get the content, all the content easily. Okay, so itu saja daripada kami hari ini. Sebelum itu cikgu berikan dahulu dua kod yang terakhir iaitu 28. Okay, 28. Okay, jadi cikgu Kop akan kongsikan link sijil dan link rekod kredit untuk pelajar-pelajar isikan menggunakan email EDD ataupun email Jawi, MyGuru ataupun email MOE. Jadi rasanya itu saja daripada kami. Sekarang pun menghampiri 3.30 petang. Saya selaku moderator Cikgu Hasmita ingin memohon maaf sekiranya ada apa-apa kesilapan dan silap susu kata sepanjang kami mengendalikan kelas pada petang ini, dan diharap semoga apa yang dikongsikan oleh Mr.Peh tadi memberi manfaat kepada semua pelajar yang mengikuti kelas kita pada petang ini. Jadi jangan lupa bersama kami lagi minggu hadapan dengan tajuk yang seterusnya, sama ada untuk tingkatan 4, slotnya adalah Jumaat 9.30 malam. Minggu depan presenternya adalah Cikgu Rina membincangkan 4.2 iaitu muatan haba tentu. Okey, spesifik heat capacity. Manakala untuk tingkatan 5 akan kembali bersama saya Cikgu Hasmita, iaitu tajuk yang kedua 4.2 electromagnetic induction. Jadi sekian dulu daripada kami. Jumpa lagi dalam siri-siri yang seterusnya. Teruskan menyokong Akademi YouTuber. Bye-bye. Assalamualaikum dan jumpa lagi.
Berita baik untuk semua. Kini Akademi YouTuber memperkenalkan sistem mata gancaran kredit AYU untuk dikumpul. Jom ikuti kelas tuition live AYU untuk mengumpul kredit AYU dan berpeluang menebus hadiah-hadiah yang menarik. Hadiah bernilai lebih RM10,000 disediakan secara percuma untuk pelajar seluruh Malaysia. Apa tunggu lagi? Tebus ganjaran hebat ini sekarang. Layari www.academyyoutuber.com untuk maklumat lanjut.
Dibawakan kepada anda oleh Akademi YouTuber.